So this talk is a continuation of the one last week in which I was talking about shortest paths in ordinary unweighted graphs. We're slightly out of phase with the lecture notes because I wanted to spend a bit more time than usual talking about that special case of shortest paths in ordinary graphs. This week we'll be doing the same thing in weighted graphs starting now. And I'll be describing the celebrated algorithm of Dijkstra, which you may or may not know, for finding shortest paths in weighted graphs. If the graphs are not weighted, or equivalently if you count each edge as one, then Dijkstra's algorithm still makes sense, but it simply reduces to an ordinary breadth-first search, as I explained last time. In the general case, it's a bit more complicated, but it's still basically a breadth-first search in the sense you look at adjacent vertices, but you actually change the priority in the queue. So you look at all the labels and you choose a vertex with the smallest label and you bring that to the top of the queue, as I'll explain now. So I want to start then today talking about weighted graphs, and this concept is very easy. It just means we have an ordinary graph and we assign to each edge a weight. It's called a weight, but I tend to think of it as a distance. Or you can think of it in some situations, it might be like a time, like in the lecture notes, there's a map of the underground with walking times between stations, which might be more relevant nowadays than it was before. So we assign a number, weight. For our examples, it will typically be an integer, has to be a non-zero, positive integer, a positive number in general. So assigning the weight to each edge means that we have a mapping D, D stands for distance, from the set of edges, which should be here E, not R, from the set of edges E to the positive real numbers. And as I say, you can think of that. I tend to think of this weight as length or distance, but it can have other interpretations. So I'll be talking equivalently about length or distance. So having assigned a weight, and that just means putting a number on the edges of each edge of a graph, we can obviously define the length of a path. The length of a path is simply the sum of, if you go along a path, that means a sequence of edges. So you just sum up the lengths or the weights of the edges you encounter. So if you really want to see that written in symbols, it's simply saying that if we have a path from some initial vertex u will always be for me the initial vertex today, to some final vertex v. So a path is just a sequence of edges. The arrows are really just for psychological comfort here. The length or the total weight, I'll sometimes say the total weight of such a path is simply the sum of the weights. So in this case, we have k things to sum up from I going from 0 to k minus 1. So we're just taking the weights associated to this edge plus this edge and so on. And that's the total weight or the length of the path. And having made that definition, we can look at different paths that go between the same vertices. So here's one path. We may have another path going between u and v like that. And we can look at the length of that other path and we can compare them, and we take the minimum of those lengths, and that would be the shortest distance between u and v. Shortest distance, or simply the distance if you like. It's the minimum. You take all the possible paths from u to v, there'll be finitely many, and you take the least lengths of those paths. I think it's clear in the examples what would be going on. So that's the definition really of a weighted graph. We're going to see an example later. I've decided today to sort of do the theory first, so you may have to, it may be a little bit obscure what I'm going to reveal next, but you can look at the example that follows on the next slide and then go back maybe and look at this. I've tried to sort of explain Dijkstra's algorithm in this single page, which is obviously not an easy thing to do. So let's say this, that Dijkstra's algorithm, as we did in the last talk, we want to find these shortest distances from some fixed starting vertex to make it easier. So we're fixing a starting vertex. So I could have called this S for start. Here I call it U. So as before, we want to find the shortest distances from that start to all the other vertices of the graph. And it will turn out, if we need it, we can also, having done the algorithm, we can actually quite easily find a spanning tree that corresponds to the search we did and the queue we eventually formed. And this is like the BFS tree I found before, but it's different because of the weights. So, as I say, we'll be looking at adjacent vertices, but we'll be sort of reordering them, as you'll see. So here is sort of a summary of how the algorithm works. So I'll explain it now, but you should try it yourself. It's really quite easy and fun to do, and then come back and look at this or read it. There's more detail in the notes, obviously, in 7.3. This is really explained in section 7.3 of the notes. There is a sort of proof that it works in section 8.1, but I tried to do a proof in the simple case of an unweighted graph, and the ideas are very similar. So I would ask you to look at that first if you haven't already seen the previous video. So here's the idea that, remember what we did before. We started from the start vertex and we looked at all the adjacent vertices. We labelled them with the step needed, and then we went to all adjacent vertices of those, and they would require 2 steps. And then we kept going like a wave moving forward through the graph, a sort of wave front, if you like, taking in more and more vertices. And we just had to make sure to label all the adjacent ones of the adjacent ones before we went to the next adjacent ones. And having done it in that way, we never needed to change all the labels. You get a tree, and if you understand that process, that you get a tree, it's sort of then obvious, although I gave some sort of proof, it's then obvious that the labels you write down are the correct shortest distances. Here it's going to be more complicated because we need to change the labels because we have weights. It may be that when we move our wave front forward, so to speak, we find a shorter path, not because it takes less steps, but because the sum of the weights is less. So that's why we have to relabel the the approximate shortest distances to each vertex as we go along. So we do this labeling, and it will be clear how that works from the example. But having seen at a certain stage of the process, some of the vertices are labelled. Some have been sort of confirmed as correct, just as before we sort of did a stage and then we looked at the next ones. But when you look at the ones that are sort of unconfirmed, you take the one with the least label. The labels are sort of a guess of the shortest distance, but not necessarily the correct guess. So you look at the smallest label, and then that will be correct. The smallest label, which is a sort of guess for the shortest distance, will be the correct shortest distance. So you sort of, I think of moving that to the left-hand side and thinking that as a permanent vertex and permanent label, and then you can go on. So the idea is that each stage it's like that vertex has jumped the queue. It might not have been the first vertex you put on the queue, but because it's labelled as least, it jumps to the top of the queue, and that's the vertex you use to then look at the next set of adjacent vertices. So this vertex with the least label is sort of symbolically put on the left-hand side and used to scan the next set of adjacent vertices. And when you do that scanning, you may be able to update the labels if you find a shorter path using that vertex. So here's the key formula. And as I say, I don't expect you necessarily to understand this as it's written now, but I would like you to look at this again when you've seen the method work. So at each stage, we have the sort of picture is something like this, that we have our initial vertex U, we're starting from, that's the start if you like, and we have just pulled out from the graph a vertex with least label, and that's called V. And we now know that means we do actually know that its label is the correct shortest distance from U to V. So there will be some path from U to V, which we can be certain is a shortest path. And then we use V, which is sort of come in from we've moved it maybe from some other part of the graph, but we now use V to scan all the adjacent vertices, including this vertex W we're talking about in this formula. So there's a single edge from V to W. And I'm sort of thinking really if the vertices of the graph is being divided into two parts. There are the so-called permanent vertices on the left-hand side of the graph. So write it here, excuse that. And the temporary vertices these are on the left-hand side, the temporary vertices on the right-hand side with a sort of division in between. Of course, when you have an actual example, you can't divide the vertices like that, but you can think of them as divided like that. So we've just moved V over from the set of temporary vertices and pulled it over symbolically to the left-hand side. And we're now using V to scan other vertices. And in particular, we have this vertex W here, and we have an estimate for the shortest distance from U to W. That estimate is the current label or the old label on W. But if, having looked at this new path that goes from U through V, then one extra edge to W, if that is a shorter distance, we update this label with this new label, in which instead of taking the old label, we're taking the length of this path, which is simply the length, the shortest distance from U to V, plus, it's not plus 1, it's plus the weight of this edge, which is d of VW. Okay, and that will give, that means we do have a path from U to W with this total weight, or with this length. So if that was better than the length, smaller than the length we had before, we use this one. And that will be a better approximation to the actual shortest distance from U to W. But it still might not be correct, because there may be some other path which goes all the way around the graph, like in the last lecture, that actually, although it has more edges maybe, possibly, it actually could have smaller weight to W. Maybe we haven't found that path yet. So we have to keep doing this sort of reduction, it's called relaxation process of updating the labels. And then eventually when W has the least label, or when we find a vertex with the least label on the right hand side, we move that over and continue the process. That's Dijkstra's algorithm. Okay, so what does that mean in about the set of vertices? Well, it means that at each stage of the game, which is a game in some sense, at each stage we've divided the vertices into two subsets, two disjoint subsets. There are the permanent vertices, which I put here, I've thought of on the left-hand side, and there are the temporary vertices on the right-hand side. If a vertex is permanent, it means it's sort of come out of the queue. And its label it comes out of the queue with a label, with the latest label it was assigned, and that label is the correct shortest distance. That's what it means to be permanent. It's really the label that's permanent. We've correctly found its shortest distance, if you believe the algorithm works. So those are the permanent vertices. Then there are the temporary vertices, which are really of two types. There are the ones that have been spotted by some vertex. There are ones that are adjacent to some permanent vertex, and they have a label, but it's not necessarily at this stage the correct shortest distance. It would be if that's the least label amongst the temporary ones. Okay, so those are the temporary vertices, and then there are some vertices we haven't even seen yet, and there's no particular name for those. But in the literature, so let me say at this point that Dijkstra's algorithm is really the basis of all these sort of modern algorithms like used in Google Maps and sat-navs and so on. They use a slightly more complicated setup called the A* algorithm. Okay, but it's basically Dijkstra's algorithm, in which, I mean, Dijkstra's algorithm is based upon this function of the shortest distance. So you estimate the shortest distance from you to a vertex, and you keep updating that. For the A-star algorithm, you add on another term, which is a sort of easier term. It's just maybe the actual distance from your vertex to the finish point. It's called a heuristic function. So you actually take the sum of the shortest distance function, which you keep updating, with this heuristic function, and it turns out that gives you a good way of finding shortest paths in practice. So in literature on the A-star algorithm, you may see other terminology. So, for example, the set of permanent vertices, they form what's called the closed set, because you've closed the account, so to speak, and the labels, you've correctly found the shortest distances. The labels of the temporary vertices, the ones that have been visited or scanned or seen, the ones with a label, with a finite label, form what is called the open set. Right, useful terminology to sort of help understand how the algorithm's working. And then there are the vertices which you haven't yet you haven't even seen. I mean, at the start, we only start with you, and every other vertex has been unvisited. What one does sort of formally is give them a label of infinity, so that this formula works here. Because if all the other vertices start with infinity, then as soon as you scan one, the minimum will be that new. when you, for example, just look at one edge, then you won't have this. You'll just have the weight going from you to the first vertex, and that will be less than infinity. So that becomes the new approximate shortest distance. So traditionally, and this is the way it's explained in the notes, you should, sort of formally speaking, put infinity as the initial shortest distance from you to a vertex which hasn't been spotted, so to speak. So the set of vertices labelled infinity doesn't have a name. I'm going to call it the dark set. Dark because it hasn't been seen yet by the permanent vertices. So this is my terminology. The others are fairly standard. In fact, there's a nice sort of little old video clip by someone I put the link on, keeps explaining the A-star algorithm. And it's a nice, although it's slightly different, it sort of makes you understand a bit more in practice how Dijkstra's algorithm works. And then, of course, as I say, you keep moving the vertices from the temporary camp to the permanent camp. So you keep at each stage, just as we did before. We're labelling more and more vertices, and as you label, we're sort of getting close to the end. And when all the labels have become permanent, obviously you've finished the algorithm. You can then find the tree I was talking about by sort of adding the edges which were used to define the permanent vertices. And that means you add an edge essentially if it joins, if the weight of the edge is the same as the difference of the permanent labels, and making sure you don't get any cycles. But I'll show you that in an example. So here's the same graph again. I had to stop the recording to cook up the weights. So I've taken the same graph from the last talk. Remember, the printed version had arrows on it, but the arrows have no significance. I've tried to obscure them. That's a bit of a mess, but I've also put weights on the edges, and just to choose weights, I chose roughly the length, relative length of the arcs, of the various arcs. So these long arcs that went round the outside or at the top, they have longer weights, bigger weights, I should say. I'm thinking of weights as distance. The two initial edges from the start is this vertex bottom left as before. They do, like we had before, they just have weight 1 as if they were a single edge. So right at the very start, we'll see no difference. But now I want to apply the Dijkstra's algorithm to find the shortest paths, or really the shortest distances, I should say, from the start to all the other vertices. So let me just make a start and try and explain how this relates to what I said on the previous slide. Okay, so obviously I can start very quickly. Obviously there's zero distance from the start to itself. There's going to be one distance of 1, not because there's one edge, but because the weight is 1, and similarly here, a 2, because you add up the 2 weights, which comes to 2. Now we have to, as before, we scan from this vertex. There are 3 vertices adjacent to 2. There's this one first of all, but instead of writing 3 as I did before, I have to take the sum of the weights. So what I'm really doing is I don't go all the way back to the beginning. I just look at this label, which is 2, and I add on the 4, and so that gives me a 6. So temporarily I write a 6 there. That will be the permanent label, but we don't know that, formally speaking. So I just write a 6 there as a temporary label. Similarly, I can have 2 plus 8, which gives me a 10 here. That becomes a temporary label of 10. And then remember, we're going all the way around the outside. So 2 plus 12 makes that vertex temporarily 14. So that does, we've now finished scanning from vertex 2. And now the key thing is this, that whereas before I could just choose of the 3 vertices I've just added, I could just choose them in any order. This time we can't choose them in any order. I have to choose the one with the least label, and that is the 6. So this 6, see what's happened so far is that in terms of my previous slide, I can think of the vertices below the pen as permanent vertices. We're absolutely certain that the labels I've written are the correct labels, the correct shortest distances. So we take this last one we added and we scan the vertices adjacent to that, and we put these labels on, which is the sum of the distance to this vertex plus the weight, each weight in turn. And then what we do, we have a number of temporary labels, namely the 3 here, and we take the least one. So we've got the so-called closed set below the pen. We've got the open set consisting of these 3 labelled vertices here, and then the other vertices we haven't seen yet, so they form what I call the dark set. But anyway, we now look at the temporary labels and we choose the least, which is 6, and that becomes permanent. So that's sort of moved, I can't physically do it, but that would sort of be moved below the pen, so to speak. And then we start scanning from 6. So let me start scanning from 6, and we've got 4 vertices adjacent to 6, so we just have to add 6 to the weights. So this becomes 7, this becomes 7, this becomes 8, this becomes 8, and now we've scanned everything from the 6. So remember before this was a 3, and all these adjacent vertices had 4, because the weights were effectively 1 in that case, but now we've got different weights, so we get 2 different numbers. Now what we do is we've got now more temporary labels, and we look again for the least, or one of the least. It doesn't matter which one we choose. The 7 is the least label, so we choose one of the 7s. Let's choose this one. That becomes permanent, and we then look at we use this to what's called scan its adjacent vertices. So there's one here, so we put a 9 there, 7 plus 2, 7 plus 2, that becomes a 9. And that deals with, and there's one more here, there's another 9 there adjacent to the 7. Of course, there's no point changing this one, this is permanent and correct. So we've now dealt with the 7, that's 7. We've got another 7 here, so the next smallest vertex label is again a 7. So we then have to scan from this 7. Well, 7 plus 2 is 9. That won't improve on this 9, so we can leave the 9. So in the previous slide, if I used the formula with the minimum, the 2 numbers would be the same. A 9 was the old label, 7 plus 2 also gives a 9, so the minimum is 9, so the 9 remains. Now we look at the next smallest number, or one of them. There are 2 8s, so let's choose this one to make permanent. So there's an 8 there. Well, 8 plus 1 is 9 again, so we don't have to change that, so that deals with the 8. That 8, and then we've got another 8, it's going to be more complicated. So this 8 is made permanent, and 8 plus 2 is 10. That's going to stay permanent, I think. 8 plus 1 is 9. 8 plus 4 is 12. That doesn't improve on the 10, so the 10 persists. 8 plus 6 is 14. 8 plus 5 is 13. Now that's significant. 8 plus 5, I'm going this way, 8 plus 5 is 13, and that improves on the 14. So the minimum in this case of the shortest distance plus the new way is 13, which is less than the old label of 14. So in this situation, if this were vertex W, 14 was the sort of old label, and 13 is the new label, which is the minimum of 8 plus 5 and the old label 14. So this becomes label 30. That's the sort of key step in the algorithm. That deals with the 8, I hope. I'll just check that I've done all. It's very easy to make a mistake if you don't use a table. I try and avoid using tables if I can, but if you really want to do it infallibly, you need a table. So that deals with that 8, and where have we got to? We can now pass to a 9. Well, let's do this 9 because there's nothing joined to it, so that easily becomes permanent. This 9 will become permanent without us doing anything else. This 9 here, we can choose the 9s in any order. The 9 here is adjacent to a couple of things. 9 and 2 is 11. 9 and 10 is 19, which is much bigger than 13, so we don't have to do anything there. And then we've got another 9, so that deals with this 9. Then we've got another 9 here. Make that permanent because it's the least label. When I make something permanent, I'm declaring, the algorithm is telling me that the label is the correct shortest distance from the start. There's no shorter path to get to this vertex than with total weight 9, distance 9. So from this vertex, we've only got one temporary label, which is 10, which is less than 12, so don't have to change anything there. Now I go to the 10, let's do this 10, that's obviously going to be permanent. This 10 here, I can make, because it's the least label, I know that this is the correct shortest distance, 10. And now it's more interesting because I've still got one label to scan from 10, it's this 13, but I can get to this vertex now in 11 steps, 11, in distance 11 I should say, because I can go all the way up here from the start in 10, and another weight of 1, it's not one edge, it's a weight of 1, would give me 11. So this 13 gets wiped out yet again, and the new label is 11. Okay, so this vertex now has an 11. So that does the 10, and I've got an 11 here. Let's start with this one. That can be made permanent, nothing more to do. 11 plus 5 is 16, which is bigger than 14. Now I have to look at this label, this vertex here. That's now the least label, there are only 2 left. So that becomes permanent. So finally we've found the correct shortest distance to that vertex, it's 11. Okay, and having seen that, we have to scan, there's still this vertex which is adjacent, and 11 plus 2 is 13. So this 14 gets wiped out and the new label is 13. And at this point, we're now finished, or almost finished, because this final temporary label, no dark labels, no dark vertices left. This final temporary label becomes permanent, so we write 13 inside the circle, and that will be the correct shortest distance attained via 11, not via however it was before. 14 was from the 8. We can get better, we can get the 13 from the 11. So I've now found all the shortest distances. More complicated than before because there was this relabeling, and this idea of relabeling is a common feature of certain algorithms. We'll be doing relabeling when we talk about flows next week. It's important to sort of understand this idea of putting labels and updating them by this sort of so-called relaxation process where appropriate. Okay, so now I want to really finish by talking about the tree. I told you that you could, again, find a sort of search tree that sort of encodes the shortest path. So I've just found the shortest distances, but in fact we did find the shortest paths implicitly because For example, in the last step, I was saying that we get to the 13 via the 11. So I'm saying that the shortest path to this vertex included this edge here. Okay, so if we want to do the shortest path, we know that this would be part of a shortest path, this edge here. And how did we get to the 11? Well, we got to it by, how did we get to the 11? By the 10, actually. We got to the 11 from the 10. But I'm going backwards. I really should work forwards. So let me see if I can do this forwards. Now, the only problem is I may forget this time. It's more tricky now. I may forget what choices I made. It doesn't really matter because you can, you just have to make sure that when you put an edge in the tree, the weight of that edge is the difference of the two permanent labels. So certainly, obviously, we have to start the tree there. We're starting again from this vertex. Now, the 2, there's no ambiguity here because 2 to 6 is 4. See, 2 to 10 is 8, so the difference between the two labels is 8, so I can put that in, make sure I don't get any cycles. Now, the 2 to the 11, the difference is 9, which is not 12, so that reminding me I can't put this edge on. If I did it, I'd get a cycle. And then what did we do from 6? Well, we went 6 to 7, 6 to 7, 6 to 8, 6 to 8. Again, the difference is always the weight, so that's okay. And then where did we go? We went to a 7. Obviously, we need this edge to get to the 9. We went from up to there, and then we went to the other 7 to go to this 9. And then we looked at the 8s. I started with this 8, I think. I didn't put the edge here because we'd already scanned that and it was already a 9, so I didn't need to do anything. So that's why I don't put an edge here. Obviously, if I did, I'd get a cycle. This edge here, obviously, to get to these two vertices, we need the edges in the tree. Then we went to the 9s. And here I've forgotten what 9 I looked at first. Maybe I did that one first. There's nothing to add in terms of edges. Then we had a 9 to a 2 to give an 11. 9, I'd already, well, I hadn't got there actually, but we never went round here because the number was too big because we'd already gone another way. So now I'm getting a bit stuck, but I want to see what other edges we need. 9, 10. Well, I've already put the one here. So what vertices am I missing? Perhaps I've got all the vertices. Have I got an edge to every vertex? Let's see what's in the tree. 6, 8, 9, 10, 7. I've got all the vertices, so there should be exactly. There were 17 vertices as I remember it, so this should be a tree with 16 edges. Let's check that. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. That looks right. And this tree contains they won't be all unique, but it contains shortest paths to each vertex. I know that's the case because, as I said, all the edges I've added have the property that the difference of the two distances, remember all these black distances are the shortest distances. And if you take any path, for example, let's choose this 9 here, say. If I want to get to the 9, how does the tree get to the 9? Well, I'm just going up this way. So it's 1 plus 1 plus 4. That's 6, 7, 8, 9. And because the difference of the permanent labels is the weight of the edge, I know that the length of this path is 9. So any vertex I want to get to using this green tree will be a shortest path. The 13, I explained it before. It was obtained by getting to the 10, then the 11, and then the 12, 13.